Imagine a machine that can peer inside the very building blocks of matter, revealing the secrets of drug molecules, biological tissues, and advanced materials. Now, what if I told you this machine, which is currently the size of a football stadium, could soon fit on your tabletop? It sounds like science fiction, but my colleagues and I have found a way to make it a reality. Currently, to produce the intense X-rays needed for this kind of groundbreaking research, scientists rely on enormous facilities called synchrotron light sources. Think of massive rings, miles long, where particles are accelerated to nearly the speed of light. The Large Hadron Collider at CERN, for example, is a staggering 17 miles in circumference. Getting time on one of these machines is incredibly competitive. Researchers often wait months for just a few precious hours of access. But what if we could change all of that? Our new research, which is set to be published in the prestigious journal Physical Review Letters, shows how we can generate these same brilliant, high-energy X-rays using a device that fits on a microchip. This isn't just about making things smaller. It's about making world-class science accessible to everyone, everywhere. We're talking about a potential revolution in medicine, materials science, and countless other fields. So, how do we shrink a stadium-sized machine onto a chip smaller than the width of a human hair? The secret lies in a fascinating property of light and some truly remarkable nanomaterials. We start with a special kind of laser light, one that twists as it moves, like a corkscrew. This is called circularly polarized light. We then fire this twisting laser pulse into an incredibly tiny, hollow tube. These aren't just any tubes, they're carbon nanotubes, cylindrical structures made of carbon atoms arranged in a perfect hexagonal pattern. They are unbelievably strong and can withstand electric fields hundreds of times more powerful than anything used in conventional accelerators today. We can even grow them vertically, creating a dense forest of perfectly aligned, hollow tubes on a chip. When our corkscrew of laser light enters one of these nanotubes, something amazing happens. The light wave clings to the inner surface of the tube, creating what physicists call a surface plasma polariton. This swirling, energetic field acts like a miniature vortex, grabbing free electrons inside the tube and accelerating them in a tight spiral motion. As these electrons spiral faster and faster, they begin to move in perfect sync, like a disciplined marching band. This synchronized movement causes them to emit their own radiation-powerful X-rays coherently. This coherence is key. It dramatically amplifies the intensity of the light, making it incredibly bright and powerful. Essentially, my team and I have designed a microscopic synchrotron, all the same physical principles that drive those mile-long facilities are now playing out on a nanoscopic stage. The unique, hollow structure of the carbon nanotube is perfectly matched to the twisting shape of the laser light. It's like a key fitting into a lock, which is why we call this a quantum lock and key mechanism. Our 3D simulations, led by my colleague Bafeng Lei, have shown that this interaction can produce electric fields of several teravolts per meter. That's 1 trillion volts per meter. To put that in perspective, it's a level of performance far beyond what even the most advanced, large-scale accelerator technologies can achieve today. Think about what this means. This isn't just an incremental improvement, it's a paradigm shift. This tabletop accelerator could bring the power of a national synchrotron facility into individual hospitals, university labs, and industrial research centers. In medicine, this could lead to much clearer and safer mammograms, or entirely new imaging techniques that let doctors see soft tissues in unprecedented detail without needing to inject contrast agents. Imagine being able to spot diseases earlier and more accurately than ever before. In drug development, researchers could analyze the intricate structures of proteins right in their own labs. This would dramatically speed up the process of designing and testing new, life-saving therapies. The next big cure could be discovered years sooner. And in materials science and electronics, engineers could perform high-speed, non-destructive testing of delicate components This would ensure the quality and reliability of the next generation of smartphones, computers, and other advanced technologies. Of course, we're still in the early stages. Right now, this all exists in our computer simulations. But the exciting part is that all the necessary components are already available. Powerful circularly polarized lasers and precisely fabricated carbon nanotube structures are standard tools in many advanced research labs. We're not waiting for some future technological breakthrough to build this. The pieces are already on the table. We recently presented our findings at the 2025 NanoAC workshop in Liverpool, an event focused on nanotechnology and accelerator physics. The response was incredible. The next logical step is to move from simulation to reality to build a prototype and conduct the first experimental verification. If these experiments are successful, it will mark the dawn of a new era of ultra-compact radiation sources. What truly excites me about this isn't just the amazing physics, but what it represents for the future of science. For decades, large-scale accelerators have been the engines of scientific discovery, but their very size and cost have made them exclusive. They are temples of science, accessible only to a select few. Our miniaturized accelerator promises to democratize this power. It could put frontier science into the hands of many more researchers, innovators, and students around the world. The future of particle acceleration will likely involve both extremes. We'll still need very large, powerful machines to push the boundaries of discovery and explore the fundamental nature of the universe. But alongside them, we will have these smaller, smarter, and more accessible accelerators, bringing revolutionary capabilities to an entirely new generation of scientists. This technology could spark a wave of innovation across countless fields. And I can't wait to see what the world will build with it. Thanks for watching.